Okay, so welcome to Math 313. This is class 15. This is the day before Pi Day. And so since we do not have class on Pi Day, I thought we would talk a little bit about Pi today. I was originally supposed to go to the elementary school and talk to them about Pi, and I was trying to think of how to do these things without knowledge of calculus and infinite series, and basically said, well, I can teach them infinite series, that's not too bad. But looking at the 2 feet of snow we are predicted to get tomorrow, I don't think it really matters how I prepare my lecture, because I don't think I'm giving it. So I will definitely be using calculus today. And one of the reasons I want to do this is I want to segue into the next unit, which is basically calculus problems. It's looking at integrals and trying to get a sense of what is the size, what is the order of this integral. This is extremely important because a lot of times we use these integrals to represent things we care about. And we want to get a sense of what is their size. This is one of the most useful things I need to do. Before we do this, of course, we should finish the Conway checker problem, which is absolutely phenomenal. So the Conway checker problem. And again, we spent a lot of time discussing this yesterday, trying to get a sense of how you would come up with the idea of associating the monovariant he did. This is the hardest part. It's the same as finding the boxes and the pigeonhole problems. There are certain problems where it's very straightforward as to what the box is, what the monovariant is. I think on the homework problem I give you a hint. Look at this as a monovariant. I might not have. I can't remember how I phrased it on the Zeckendorf decomposition. But here you get the line y equals 5, y equals 4, y equals 3, y equals 2, y equals 1, y equals 0, y equals -1. And you start off with infinitely many checkers below. And after a while, we decided to attach a monovariant. We were trying to prove that you can't get to this special place right here. And we said, without loss of generality, this might as well be the point 0, 5. And we're going to somehow measure how far we are from each. And we need to have weights, because otherwise things won't converge, because we have infinitely many objects. So again, the more you stare at the problem, the more natural these things become. We could have actually had 2 weights, one weight for the x direction, one weight for the y direction. Turns out you can use the same weight in both directions. And we're going to use the taxicab metric. So the taxicab metric is extremely useful if you are talking about grids like Manhattan, where you can only move east, west, north, south. And so the distance between 2 points is just how many units north, how many units south. So if we are at, so the distance from, say, 0, 5 to ij is going to be negative, how do I want to do this? I plus, absolute value of I plus 5 minus j. And so, the I part is easy because if we're over here, we have to move over I steps in one of the directions. And then if we're down at j, it's going to be 5 minus j. And we want to make sure we're only dealing with positive numbers. You're not a negative distance away. And so the question is, what weight should we attach? And so we want something so that as we do the calculation, whenever we do a move, the total sum of the board is fixed or decreases. Either one is fine. So if we take a piece and we jump and we move further away from 0, 5, we're only going to decrease the total sum because we lose one piece and we gain a new piece that's further away. So the only thing we have to worry about is jumps coming closer or jumps going up. In both of them, when we do a jump going closer or a jump going up, we lose a piece and we move a piece closer. So the question is, how much of an analysis do we need to do? So the first thing is, if we have some kind of weight, if I'm using this, we'll do 1 over w, where w will be greater than 0, greater than 1. We need this whole sum to be finite. So we would want, a sum, I goes from minus infinity to infinity, a sum j goes from 0 to negative infinity, and then we would want 1 over w to the I plus 5 minus j. Well, what's nice is we can split this up, do the I sum and the j sum separately. The easiest way maybe to do the I sum is to just add in the row j equals 0 again. Maybe just add in this central column again, and then just double the columns. And then just subtract off what that is. But there's various games. It's just geometric series. So we can do the geometric series. Easiest way might be to just double this column, and then we can just say, oh, it's from here to here, and then just divide by 2, because we don't want to double count things. Okay, so you would calculate what this is. And then you would show that this sum is a monovariant. All we need to worry about is what happens if you move closer. So we could look at those different cases. Will it move today? Yes, it's going to move. So we could start off, here is 0, 5. Here's some point, say ij. And then we're going to move, here's something at I minus 1, j. And here's something at I minus 2, j. And so this is one of the moves, is we could jump over and move to here. We could also be jumping upwards. But by symmetry, if we decrease I by 2, or if we decrease j by 2, it's really going to be the same. So we only have to do one calculation. For me, it's much easier to think about looking at it in the x direction of moving closer. Everybody comfortable? OK, next thing is to say, well, since the j's are the same for all of them, I don't really have to worry about the j component. Right? And then the next thing to say is they have the same I, and then this is one more. I'm sorry, this is one less, and this is two less. So what we really can do is we can say, well, look, all I'm trying to do is show that there's been a net decrease. I don't actually have to calculate the quantity. I just have to show that it decreases. So then rather than calculating the quantity, I could multiply the quantity through by maybe like the weight squared or something like that. And so in the old, up to some constants, we had a piece here and a piece here. So if you call this, 1 over the weight from this one, and then this one was 1 power higher. So if you were maybe call the first one 1, and then, let me make sure I'm doing this in the correct direction. Do I want this to the negative 1 power? I think I want this to the negative 1 power. So we can assume that this is a weight of 1. This weight is 1 over w times that, or just w times that. Right? And again, it's up to scale. So it's 1 and w. And now in the new, we've lost both of those, and we have this piece, which would be w squared. So we want w squared to be less than 1 plus w. So w squared minus w minus 1. I'm hoping I'm doing this right. We want that to be less than 0. OK. So what does this look like? I'm sorry? Looks like the golden ratio, right? This is just the Fibonacci relation. So you would get...
It looks like you have to get w is greater than the golden ratio.
We're putting w in the denominator, so we'll have 1 over w. So, right, so we'll get w would be 1 plus root 5 over 2, as we want w to be greater than 0.
Right, but I think that if you want that on the left side.
We should actually say less than or equal to. Because if we go like this, it's OK if we don't decrease. We just have to make sure we don't increase. Because if we take this and if we jumped in the other way, we'll clearly decrease. Because then we're taking a piece, removing that piece, removing this piece, and replacing the two of them with a piece that's further away. So in some sense, ideally, in a situation like this, we'd be exactly equal to 0. And that would be the critical value we could take. And so that would be the large thing. So if you want, we could actually put an equal sign here. And since we know w has to be greater than 0, this is the Fibonacci root we want. So now we would want 1 over w, which is 2 over 1 plus root 5. Does anybody remember how to deal with something like 2 over 1 plus root 5?
Multiply by top divided by 1 minus.
Yeah, this is the old rationalize fractions where you have square roots. I think it's been a long time since you've done this. You might have done this in high school. Did people do this in high school? Middle school? Okay, good. So you've done it at some point in your life. Did you ever see a reason why you might care about that in middle school? Or was it just these cookbook problems that they want you to work on this unit?
My middle school teachers made it difficult to ever see. How they would ever care about what they were doing.
It's not just your middle school teachers. I think people should be, okay, I can't quite say shot. People should be prosecuted for forcing students to learn the quadratic formula without learning why you would care about the quadratic formula and just doing 40 problems again and again and again. So we rationalize the denominators. And now we get 1 minus 5 down below, right? So we get 2 over negative 4, 1 minus root 5. And so this becomes negative 1 plus root 5 over 2. And that's actually the quantity that they look at in the proof that I saw. And so in the book I read, they call that C. But it's just 1 over the golden mean. It's coming from the same relation as the Fibonacci's. It's because at this critical point, we want things to be equal because we know in the other directions, whenever we do those moves, it will go down. And again, I'm trying to simplify the algebra by only looking at the parts of the expressions that really matter. I'm throwing away the common multiplicative factor from all the terms to just really simplify the algebra. And because this is greater than 1, these sums are going to clearly converge. So now all we have to do is you calculate what is the value of the whole board and what's the value of the board at 1, where you have something just at 0.5. And I believe if you do the calculation, if you have one piece at 0.5, it equals the value of the initial configuration.
When W equals that?
Yes.
Really?
I believe so. Because when you have something over here, you get a value of 1. And if you calculate everything over here, I believe the sum of the initial configuration is 1. So if a piece could get all the way up here, you can only do it in finitely many moves. There has to be at least 1 point left below, which would have to give you at least a positive value, so the new configuration would be greater than 1. So all you have to do now to finish the calculation is show initial state has a value of 1. Because we know if you just have something here that has a value of 1 because the distance is 0. And now we're done. And you can see where this monovariant comes from. We could have tried to do things a little bit more generally, as I said, where you have a different component in each direction. But fortunately, we don't need to do that. OK. Any questions on this? So again, you either love problems like this or you don't. I particularly love this problem. I find this extremely ingenious, coming up with something like this. Now the question is, what could you do to make the problem harder? Instead of going to 0.5, would you try to go to 0.6 or something like that to just throw people off? I mean, the same argument would work, and you would see that's not possible there. But
0.5 is particularly cool because
yes.
the smallest value of W or the largest value of W. Or I think the largest value of W over there corresponds to the smallest value of W over there.
What do you mean by the largest value of W?
Well, you said.
Oh, the largest one we could take?
Right, yeah. That was W squared is less than 1 minus W. Was what
Right.
you initially wrote.
Right.
You made W any bigger, then inequality would no longer hold.
Correct.
So the smallest value of W over there corresponds to the
Yes.
largest possible value.
Right. And then, of course, the question is, if you did a different one where it actually now decreased if you went like that, could you still prove that things are fine? Or maybe now the new configuration would break down, and you wouldn't be able to immediately rule it out. So my feeling is if you choose a smaller value of this quantity, it's not going to work. But that's a good exercise to do. The other thing, of course, is there any connection to the 5 and the 5 over there? Is this just a coincidence? What if we had like a Fibonacci or something like that? What if we had a new rule for checker jumping? What if you had 2 checkers and you have to jump over 2 checkers? Could we get something like a Fibonacci relation, and what would go on? Or if you move diagonally. But I would say I would try a Fibonacci, that the way you jump now is we jumped over 1. Now I want to jump over 2 to an empty spot. So I think this is a really good problem. So this will almost surely become a homework problem.
Now, if you were just given the checkerboard to start with, how would you go about finding what the maximum level you could?
The maximum level. I mean, right. Well, part of it was doing the brute force, and we saw it wasn't that hard to get up to 4. Now, again, in something like this, if you don't know how high you can go, what you could do is you could say, let's assume that there's some limit. And I could just say maybe it's at L, 0L. And then keep that as a free parameter, try to do the analysis, and see what value of L is going to clearly be high enough that I won't be able to do it, and then narrow it down. But it would be interesting to look at, because the Fibonacci, which would be Tn plus 1 is Tn plus Tn minus 1 plus Tn minus 2, we can write down the roots of that explicitly. It's a cubic. There is a formula for the cubic. Are those numbers going to somehow relate to where we should go here? What if we had some other kind of, it would be interesting to see, can you put other recurrences in here? You could make it in 3 dimensions. That would be a great thing to do. So saying, I think these would be great problems. These could easily become problems for pi mu epsilon. These could easily become short little research papers. And this is one of the reasons why I'm trying to assign you, not so many homework problems, so that if you find something exciting, run with it. But I don't know if anybody's tried to look at this in 3 dimensions. I don't know if anybody's tried the Fibonacci.
For 3 dimensions, my guess the only real difference would be calculating the initial state, like the initial value.
Yeah, so the question is, does the 3rd dimension help you at all, or does it just make the problem more involved?
I mean, it makes it more impressive when you figure it out. People who haven't
No, and a lot of times when you do stuff like this, it makes it look harder, but those extra dimensions may not help.
Well, they might not help make it hard.
They might not help make it harder, but again, it's what does your intuition say? Should you be able to somehow help things? Because maybe that gives you now other pieces. Now, for instance, if we have things in this, could we somehow get things higher? Because now we could move things from the back forward. And maybe that would help us, because if we could get something in the 3rd row, we know how to get something in the 4th row, right? So we could put that above, and then we could move that up.
Yeah.
So could you climb to infinity?
My guess is you just start out with a higher value and then you'll reach a point where you get.
So I think that's a great thing to look at is, can you get to infinity? If you do this as the 3-dimensional checkerboard problem. We are really going to have an unlimited budget now. But, it's still countable, so I can shuffle things around so it doesn't really cost me anymore to go to 3 dimensions. But I don't know, because I can see now pushing things in, and maybe you can keep doing this and keep walking up. And just, how far can you move something and then slowly move it? I don't know. It's great things to think about. All right. So tomorrow is Pi Day. So in honor of Pi Day, we're going to do e to the pi versus pi to the e. So Professors Garrity and Adams here have debates as to which is better, e or pi. I can't remember who chooses which one. Does anybody remember? Okay, that makes sense, based on the fact that he would choose like the trefoil knot over the Euclidean algorithm. So the question is, of course, which is better, e or pi? I will admit I don't fall clearly on this one. Euclidean algorithm, I'm clearly supporting the Euclidean algorithm. E and pi, this one is harder. And for the record, there's a couple of other candidates. Instead of studying pi, some people study tau. Anybody know what tau is? And this is why tomorrow the pizza here is going to be at 6:28. So they're trying to basically be diplomatic here and make it acceptable to everybody who likes pi in all of its formulations. If you happen to be a tau person, you're welcome at the event. Sorry, that was just me being sick. And then there is another possibility which I've talked about. Very few people support this, but there is 4 pi. And the nice thing about 4 pi is if you're doing things in physics, you often have constants, 1 over 4 pi k naught or epsilon naught. This is coming from the surface area of the sphere. The other one which I kind of like is gamma of 1/2, which is negative 1/2 factorial, is the square root of pi. And this comes up in the normalization of the Gaussian. This is another really nice one. All right, so the goal is to discuss e to the pi versus pi to the e without using a calculator. So does anybody have any thoughts on how to elementarily attack this problem as to which one is larger? Yes?
The way that I did it was you raise both of them to the 1 over pi power.
Okay, so you're going to, so one approach is to raise to the, what is it?
The 1 over pi.
Okay, so if it's 1 over pi e, that's to the e to the pi power?
No, both of pi and e are on the denominator.
Oh, 1 over pi e, okay, to the 1 over pi e. And then you get e to the 1 over e versus pi to the 1 over pi.
And then you can just use single variable calculus.
Good, excellent. So now this is looking at the function f of x is x to the 1 over x. Or it's e to the log of x divided by x. And we want to try to figure out where's this function largest. And so now we can use one-dimensional calculus. We get f prime of x. Well, as soon as I see the exponential, I take the derivative of the exponential, which is itself, times the derivative upstairs. So I'll get f of x. And now I want the derivative of log of x over x quotient rule. So it's the derivative of log of x times x, right? So it's x minus then the derivative of x, which is 1 times log of x. Am I doing this right?
I don't think so.
No, this doesn't seem, okay, wait. So the first is, it's u over v prime is it vu prime minus u v prime over v squared? All right. The quick way to check is to write this as uv to the negative 1. And if you write it as uv to the negative 1, then yes, you'll get this. Okay, so the derivative of log of x is 1 over x. So the first term here should be 1, not x. That's why I was just looking wrong. And then the second term is u, which is log of x, times v prime, which is just 1. So it's 1 minus log of x over x squared. And so if we look at this, the f of x over x squared doesn't really matter. So this is f of x over x squared. And then we have 1 minus log of x. If you want, you can write 1 as the log of e. And this is just the same as the log of e over x. So this allows us to talk about curve sketching. So if this is, x, what you often do is you write f prime down below. So the critical point is when x equals e. And so f prime is going to be 0 at the critical point. As x goes to so if x is less than e, then this is the log of a number.
That's greater than 1.
So it's the log. So why is it greater than 1?
Because x is on the bottom and x is less than 1.
So x is less than e. So this quantity here,
Greater than 1.
the log of 2 is less than 1. The log of 2 is about 0.7. It's positive, right? So if x is less than e, we have the log of a positive number that's greater than, in fact, we have a log of a number greater than 1, so it's positive. So my derivative is positive here. Now, once x is greater than e, I have the log of a number that's less than 1, and that's going to be negative. So what this tells us is the plot of this function looks something like this, where its maximum value is at e. So the maximum value has to be 1 at e. So e to the 1 over e is greater than pi to the 1 over pi. So e to the pi beats pi to the e. So well done. Remember to email me. All right. So this is one way to elementarily attack this. A lot of the proofs I'm going to show you are very similar. Does anybody else have another way to elementarily attack this?
Can you do anything with imaginary numbers? Is that something that I thought about in my friend lab?
Okay, imaginary numbers. How would you get the imaginary numbers?
Well, I was thinking just raising everything to the i's power.
Ah.
And then seeing if you could do anything from there. But everything that I did, which wasn't very much,
Yeah.
got to like adding a rational number.
Right. Yeah. Having imaginary numbers here scares me because of how things align. It's not bad because we do have the relation e to the I pi is minus 1. And you're trying...
That's what I thought about.
Right. So if you raise it to the I, you would know that the left-hand side is of magnitude 1. But then, how does this... it's a good thing to try. And then what could we say about pi to the ei? Then this becomes e to the ei log pi. But now we have to worry about how complex numbers are. And...
Well, I was also thinking, would you be able to just look at the exponent to see which is smaller?
No, because the exponents are going to be imaginary.
But like, just see which ones, like, if you imagine the like unit circle, which one's farther along the circle, would that work, or would that be?
No, because for complex number, you can write any complex number as rho e to the I theta. Well, actually, I guess we would do r. And this part has absolute value 1. And this is where the magnitude of the number is. So as soon as you raise things to the ith power, they'll have the same magnitude. That's the problem, is the numbers will have the same magnitude, and I'm not sure how to compare them.
I was thinking, just looking at which has a greater theta.
Right, but that's not going to really, that's going to just tell you about the angle part, not about the magnitude part. And so I don't know how you then deduce that. So I wanted to show some plots. The first plot I was looking at was e to the x versus x to the e. And so just to see what value of x makes this largest. And what we want to do is we want to see, well, what happens when we put in x equals pi? Which side is larger? So the problem is if we try to plot this, it's going to look something like this. And so it's often tough to look at something like this. So if I look at the difference, so this is e to the x minus x to the e, and this is the two ones. Now, when x gets very, very large, which is going to win, e to the x or x to the e? Yeah, e to the x is going to win as you go off to infinity, because exponential growth beats polynomial growth. And as x goes to 0, x to the e goes to 0, but e to the x goes to 1. So down here, you'll also have e to the x. It's just what happens in that nether region between. And of course, they're going to be exactly equal at e, so e is going to be some kind of critical point. And this is very similar to what you were showing us over here. What's the right function to look at? There's a lot of things that are all very similar, but which is going to be best for calculus? Now, for something like this, if I look at the plot, and this is why I wanted to just print this out so I could look at it, it goes up, down, and up. And so if I start taking derivatives, if I call this f of x, then I would get f prime of x is e to the x minus e x to the e minus 1. And I can start trying to play games of dealing with that.
Why couldn't that e to the x minus x to the e is always positive except when x equals e?
Well, how do we know that? See, we don't know that e to the x is always greater than x to the e. We need to prove that. One way to prove that is to look at the value of this. Now,
Okay, so you can, but if you say that they start with e to the x greater and they end with e to the x greater, then you can look at derivatives.
right, so we would know that e to the x is winning here, it's winning in infinity, and if we can show that it comes down and the derivative is negative here and then positive here, we know the curve would have to look something like this. So if we can show that there's like 3 regions, increasing, then decreasing, then increasing, we'd be fine. Because we know at this point they're exactly equal. But the calculus is just a little bit hard. There is a way to make the calculus easier, and this is one of the reasons why I want to talk about this approach. If you take a class with me, you need to have a Pavlovian reaction whenever you see a product. If you're teaching multiplication to elementary school kids, you can resist the impulse. But that's essentially the only time I want you to resist the impulse. What should you do whenever you see a product? What should you do whenever you have a product? Do we have much experience taking products? What do we have experience working with? Yeah. Sums. How can we get from a product to a sum?
Express multiplication as a sum.
So how do we do that? What operation can we apply? What function could we apply to both sides that will convert products to sums?
Exponents.
Not exponents, other way.
Or
Logarithms. Whenever you see a product, you should have a Pavlovian response. Let me look at logarithms. Frequently, it's much easier to study the logarithms than it is to study the actual function. How many of you have taken statistics? All right, just one? Or have you taken statistics? I can tell you. All right, so if you take statistics, it's often hard to determine what a relationship looks like by hand. If I see something like this, it's hard for me to see what that curve looks like. If I have a relation, let's say I have, y equals c x to some power. If I do a log-log transform, and I look at the log of y is equal to r log of x plus the log of c, if I call these my new variables, if I call this script y equals r script x plus script c, it now becomes a line. So when you do a log-log plot, you can change a power law to something linear. And then you can deduce what the slope is, intercept here is, and extrapolate and get the main term. So we do this a lot in statistics. This is an extremely powerful observation. You really want to get used to whenever you see a product, you want to think logs. So instead of looking at the functions we had a moment ago, let's take logarithms. So if we take logarithms, we would have x, because the log of e is just 1, versus e to the log x. And of course, for us, log is always log base e. And now, if we were to do a plot, now the plots look like this. And this interception is e, and we can see, of course, x is very easy to plot. If we look at the difference, x minus e log x, it's going to look like this. And that's going to be a lot easier to analyze. It now just goes down and just goes up. This is also a much easier function to work with than what we had before. So this is one of the big ideas is how can we convert this algebra to something more tractable? So for the second approach, we will do x versus e log x. So I'll call this g of x will be x minus e log x. So g prime of x is going to be 1 minus 1 over x with an e up top. That's a nice function to work with. And so now again, how many of you have done curve sketching in calculus? Where they had you draw, here's the x-axis, here's f prime, here's f double prime. I see one person nodding, and just one person. This is now one of those lost skills. Okay. I remember being parts of the debates as to, do we still want our students to learn how to do this? Because graphing calculators, graphing programs are now so prevalent. It's nice to be able to quickly look at something and get a sense of the behavior. And so what you would often do is, here's x, and you'd be plotting f over here. Here's f prime. And sometimes you would do f double prime. And you'll find where are your critical points, where are your points of inflection, where's the function concave up, concave down, and you would take this information and build it. I'll do another problem to just show how powerful this is. So for here, the key points are 0 and e. Well, if x is less than e, this is positive. Am I doing this right? No, if x is less than e, it's negative, right? It's 0 at e, and then when x is greater than e, it's positive. So the shape of g has to look something, and we know the value of g at 0, at e. We can just plug in e to our original function. We get it is equal to 0. So we know here it is at 0. We just need that one point. And then we know the curve has to look something like this. And now we know e to the pi has to be pi to the e. So this is the second approach. I'm trying to think if I had one more calculus approach or if this was the only one. This might be the only one. Because we already did the x to the 1 over x. Yep, OK. So that's the three standard ones. There is another calculus approach to this that I really like. But I need a little bit more information. So before I go through this, everybody's comfortable with this one. All right. I need a couple of facts about e and pi. Right, so I can actually use those infinite sums to get the facts I need. I need e is less than 3, is less than pi, less than 4, and say greater than 2. I think that this should be more than enough. This is not a strong result. If we know e is the sum of 1 over n factorial, we know the series rapidly converges. It's not too bad to show it's greater than 2 and less than 3. For pi, we need to show pi is between 3 and 4. Well, if I take a circle, never draw the square first, I guess. If I take a circle of radius 1, the area of the circle is pi. The area of the square is 4. And then with a little bit of work of looking at like something inscribed over here, we can show that this is, 4 sides might not be enough. We might need to go to 6 or 8 sides. But with a little bit of work, we can show it's greater than 3. So this is not that bad of a preliminary. So we're all happy? OK.
If 2 to the 3 is less than 3 squared, why would this be enough?
I'm sorry? Oh, no. I need this fact in what I'm going to show you now. I do need to know that e is less than pi. So what I'm going to do is I'm going to basically do nothing. And so what are the two ways we know how to do nothing? We can multiply by 1 and add 0. So let's look at pi. I claim pi is the same as e plus pi minus e over e. Everybody agree that this is the same as pi? Oh, shoot. Oh, did I type it? E pi, maybe. Yeah. I'm sorry, pi over e. This would be pi over e. Sorry. No wonder people are, OK. We all agree that this is pi over e. OK. And what I can write over here, this is 1 plus pi minus e over e. And this quantity here is between 0 and 1. Pi is greater than e, so this is positive. And pi minus e over e is not going to be as large as 1. Because this is at most 4 minus 2 over something greater than 2. So this is a number between 0 and 1. And I'm going to use the log of 1 plus u is u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4, which is greater than u if 0 is less than u is less than 1. So I'm looking at the Taylor series expansion of the log of 1 plus u. And because these terms are alternating, and because u is positive and less than 1 in absolute value, these terms will be positive contributions, these terms will be negative contributions. And so if I drop from here onward, this term beats this term beats that term, I've dropped a negative sum, I've increased things. So I'm sorry, I think I want this less than u. Sorry. So I've made it larger by just dropping all that stuff over here. Okay. So now let's see how this can help us. And again, it shouldn't be surprising that we're using a logarithm because we're dealing with a function involving e. All right, so let me just set it up the way I want. So we have e to the pi versus pi to the e. If I take the log of both sides, I would have pi versus e log pi. Right? Let me see. Now I'm just wondering, because I'm afraid I might have just made a small typo. All right, so hopefully this won't be too bad. All right. So we have pi over e versus the log of pi. That's what we want to study. Okay, so I think I've actually typed things up slightly wrong in my notes, but that won't be too bad. We'll fix it right now. So we'll have pi over e versus the log of pi over e times e. We'll just multiply by 1. So we'll have pi over e versus the log of e is 1 plus the log of pi over e. All right. So now the log of pi over e is the log of 1 plus pi minus e over e. Well, we just showed that the log of 1 plus pi minus e over e, that's just our value of u. This is going to be less than u. So we get the log of pi over e is less than pi minus e over e. But we wanted to add 1 to both sides, right? So 1 plus the log of pi over e is less than 1 plus pi minus e over e. Well, what's 1 plus pi minus e over e? Pi over e. So we get 1 plus the log of pi over e is less than pi over e. And that allows us to resolve the problem. So we are able to solve this using Taylor series.
Why did we add 1 to this? Oh, never mind.
Right, we added 1 because we have to multiply by the e over e. So I had skipped that when I was writing up my notes. But fortunately, I had enormous. I was wondering why I had so much extra leeway. I think I wrote down what the actual values were for the two of them. Right. So just for the record, e to the pi is about 23.14. Pi to the e is about 22.46. So I mean, it's not an overwhelming victory. It's at least competitive. But there's a lot of really good techniques in this. The idea of a Taylor series expansion and looking at the main term, this is extremely powerful. The question is, which function do you want to work with? And again, in most of the classes you have, they give you the function. The difficulty is when you have to figure out what function do you want. This should remind you of something from geometry, right? What's the key idea in almost any difficult geometry proof? What do you have to do? Almost all difficult geometry proofs come down to doing something. Draw the right line, draw the auxiliary line. Figure out where to put the line in. Once you see the line, oh yes, that's what we're supposed to do. And then you have a couple of hints to help you figure out where to draw the lines. Can I make a right angle somehow because I like Pythagoras? Can I split something in two? Can I try to get similar triangles? You've got a bunch of things to try to help you figure out where to put those auxiliary lines. And you can maybe try this at all the different vertices. Go from vertices to edges. You won't just have like a mechanical procedure of things to try. So here, we saw lots of different calculus proofs. The calculations were very similar. We look at our two functions, we subtract them. So we now are looking at the difference, and we want to show the difference is always non-negative. And we can do that now with calculus by taking a derivative and looking for the first derivative test. Because if the first derivative is negative, the function is decreasing. If the first derivative is positive, it's increasing. Then that has to be a minimum. OK, so on Wednesday, we will continue, and we will do applications with integration. I'm not giving you stuff to read because if I give you stuff to read, I have to give you the name of the technique, and then that will tell you how to do the problem. And so I'm keeping the names of the techniques of integration secret because I don't want you to know what they are. But I will leave with just one more problem related to this. Since you guys haven't done too much curve sketching, there is a problem which essentially allows you to review all of Calc 1. It's the Calc 1 on drugs problem where you basically throw everything at it. It is solvable with Calc 1. And the problem is the following. And I want you to think about this for Wednesday. So given some number n greater than 0, decompose n to be a1 plus a2 plus an. Each ak is either, in case 1, a positive integer, or in case 2, greater than 0. And you want to maximize the product. So I want to split n into some number of pieces. In the first case, I want them to be positive integers. In the second case, I want them to be greater than 0. And I want to make the product as large as possible. You have, n is free, but an integer. You can't split something up into 3½ pieces. So what makes this problem a little bit challenging is you don't know what n is. You have some freedom in little n. So think about for Wednesday, how would you do this? How would you split this up? How would you tack it if everything's an integer? How would you tack it if everything is greater than 0? This is not a cookbook problem. This actually has applications in computer science. And it is related to the discussion we've just been having today. I don't want to say exactly to what in the discussion, because that will give things away a little bit, but it is connected to what we were doing. This is not an arbitrary problem. OK, so this is a good place to stop. Enjoy Pi Day tomorrow.